Hi, this is Basim, who's joined the graph. In this video, we will continue learning about the Gremlin traversal language and we will see examples of more complex traversals. This video series is based on the Getting Started tutorial on the Apache TinkerPop website, the one you see on my screen right now. I'll be writing the commands in this text file and I will copy and paste into the Gremlin console. After I'm done, I will upload this text file somewhere and I'll put a link in the video description. As always, we need to start by creating a graph and creating the traversal source. Usually, we do this by writing two separate commands, one to create the graph and another command to create the traversal source. But this time, let's do it a bit differently. Let's try to do it in one command. What we used to do before, we used to create the graph using something like graph equals tinkerfactory dot create modern to create an instance of the modern toy graph. And then in the next command, we create the traversal source by writing g equals graph dot traversal. But do we really need two commands for that? This graph object right here, we only use it to create the traversal source. So maybe everything can go on the same line. So in this one command, we create an instance of the modern toy graph, and we create the traversal source, and we assign it to g. So let's copy that and paste it into the console. And we just created the traversal source successfully. Now let's move to our next command. We want to get the age values of the two persons named Vedas and Marco. Before we write the traversal, let's look at our graph to remember how it looks like. So we want the ages of Vedas, this vertex right here, and Marco, this vertex. Let's try to write this traversal. We will start by writing g.v, which will get all the vertices in the graph, and then backslash to go on the next line. And now we want to filter by the values of the name properties. The only thing we know about these two people is that their names are Vedas and Marco. So to filter by property and a property value, we use the step has. So we will say .has. And I like to use the overload that takes the label as the first argument. So the labels here are person for these two vertices. We're searching people, not something else. We're not interested in these software vertices. So if there is a software called Vedas or Marco, we don't care about selecting it. This makes it more obvious what we're looking for. So person, the label person will be the first argument. And the second argument will be the property name. We want to filter by the name property because we know that the names are Marco and Vedas. So the second argument will be the property name, which is name here. And the third argument, well, we saw the has step or function before, and we used it by passing the property value as the third argument. But in this traversal, it's a bit different because we don't have a specific property value. We know that the property value should be either Vedas or Marco. So really what we have here is a predicate, not a fixed value. So how do we tell Gremlin that the value of the name should be either Vedas or Marco? Well, to do that, we use the function within. And within takes the possible values for this property. Vedas is one of the possible value and Marco is the other possible value. And this will be this within function will return a predicate that will be used by the has step to filter the vertices. And it looks a little bit strange just calling within like that. Like where is this within function? Where is it defined? Well, this within function is actually a static function of the class P. So we can say P dot within to get this predicate. But since the members of the P class are statically imported by the Gremlin console, We don't need to prefix the function within with a class name. You can just call within by its name like that. Okay, so this will get us these two vertices, Marco vertex and Vedas vertex. But we don't want the vertices, we want the values of their age properties. So to get the value of a property, first I'll put a backslash to go on a new line, and then I'll use the step values to get the values of a certain property. Here the property we are interested in is the age property. Okay, so this will get us the ages of Vedas and Marco. Just to be certain, let's test it in the console. And it did get us 29 and 27, which are the expected values. 29 is the age of Marco, 27 is the age of Vedas. So let's move to the next traversal. Get the mean of the age values of the two persons named Vedas and Marco. Well, this is almost like the previous traversal, except instead of getting the list of the ages, now we want to get the mean, the average of these ages, like their sum divided by their count. So the start will be just like the start of the previous traversal. Up to this point, we have a list of ages. Then we want to get the mean of these ages. So I'll write the backslash and I will add the step mean. This will get us the mean of the list of values returned by the previous step. Let's test that in the console. And we got 28, which is the mean of 29 and 27. Now let's move to the next traversal. We want to get the names of the persons that Marco created software with. And I will start by showing you a flawed, imperfect version of this traversal, and then later I'll show you a better version. So to get the names of the persons that Marco created software with, we need to start by finding Marco, the vertex representing Marco. So we will say g dot v, and this will get us all the vertices in the graph. This will place a gremlin on each of these 6 vertices. And then we want to filter them and keep only the gremlin that's on the Marco vertex. And the only thing we know about this vertex is the value of name. We want to remove all the gremlins that are not on a person vertex named Marco. So to do that, we will use the has function. Has is what we use whenever we want to filter by property. First argument to has will be the vertex label, person in this case. Second argument, the property name, which is name. And third argument will be the value of the name property. We're looking for Marco. So this will remove all the gremlins and will keep only the gremlin on the Marco vertex. Next, we need to find the software that was created by Marco. And that's our step towards finding the people that are collaborating with Marco on the same software. So to find the software that was created by Marco, we need to move out along this created edge to go to the software that was created by Marco. We're not interested in these edges, the people that Marco knows. Those are not relevant in this case. We only care about the software that's created by Marco. So we will move out along the edge created. And this will move the gremlin that was on the Marco vertex. It will move it to this software, this LOP software vertex. So at this point, the gremlin is right here on vertex 3, representing the software that was created by Marco. Next step, we want to move to the people who are creating the same, who are helping Marco create the same software. So we need to move along this created edge going into the software vertex. There are 3 people working on the same software. There is Marco, which is the vertex we came from. There is also Peter. He's helping Marco create the same software. We see this edge connecting Peter to the same software. And also Josh is working on the same software. So we need to move along these created edges towards the people who are creating it. We need to move in the opposite direction of the arrow. To do that, we would use the in function, in created. So out moves us in the direction of the arrow. The in function moves us the opposite direction of the arrow. So this gremlin will be split into three gremlins for the three people who are collaborating on this software. One will go back to Marco, and the other will go to Peter, and the third gremlin will be on Josh. So now we got to the people who are collaborating on the software. We don't want the vertices. Right now we have a list of vertices, like the result of this last step of this in step is a list of the vertices, but this is not what we want. We want the names of these people. So this is easy. We'll just use dot values to get the values of their names. And this should get us the names of the people who are working on this software. I will test this in the console. And we got Marco, Josh, and Peter. Okay, this version is imperfect because the original question was, who are the people who are collaborating with Marco? So obviously we don't want Marco in the result. We only want the people who are helping him create the software. So is there a way to exclude Marco from the result set? Let's try to do that. And this will be our good version, our better version. So I'll start by copying the command we just wrote. And let's look at what we can do to enhance it. What can we do to filter Marco and exclude it from our result? Well, at this point right here, we have the Marco vertex. So let's give the result of this step a name so we can refer to it later and exclude it from the result. And to give the result of a step a name, we use the as step modulator, the as function. And as will save the result of the last step and give it a name. The argument to as is the name that will be used to save the result of the previous step. And let's give it the name here, exclude. So the result of this has step will be saved and will be named exclude. And we can refer to this exclude variable or saved value later to do anything with it. Well, what do we want to do with this exclude value that we just saved? And you know what, before I move on, let's try to picture this on the graph. So I'll first delete the first gremlin. So we said g.v places a gremlin on each of these 6 vertices. Has will filter these gremlins and only the one on Marco will remain. So we will have a gremlin on Marco right here. And what does the as is called the step modulator. It doesn't really move the gremlin or filter it or do anything like that. It just gives a meaning or adds information to the previous step. Here it saved the result of the previous step using the name exclude. So this gremlin right here, we asked this gremlin to remember the result of the previous step and give it the name exclude. So this gremlin in its little head, let me write, will save a variable called exclude, and the value of exclude will be the result of the previous step, the vertex it's on right now, which is v1. So this will be saved in Gremlin's memory, and whatever is saved in his memory will move along with him. So that's what as did. Then the next step is the out step, out along the edge created. This will move the gremlin and whatever is saved in his memory to the software that Marco created. And then later the in step will move the gremlin in the opposite direction of these created vertices. So just like before, one will go back to Marco, one will go to Peter, and this one will go to Josh. And at this point, we want to keep these two gremlins and we want to remove this one because Marco's where we came from. We already know that Marco's collaborating with himself. He's already working on this software. We just want these other two people. So how can we exclude Marco with the help of this value that's saved in the gremlin's head? For that, we can use the step where. Where is another filter step just like the has step, except the has step, it filters by a property value. Where filters by the object itself, the object returned by the previous step. And the object returned by the previous step here are the three vertices. So we will call where, and we will pass the argument, which will be a predicate, not equal in this case. And not equal can take the name or the key of the value that's saved in Gremlin's memory, exclude. So this will filter these gremlins by the ones that are not equal to the value saved and exclude. So this gremlin will test the predicate. This one right here will test the predicate. Is your current vertex equal to the value saved and exclude? Yes, because it's currently on vertex 1 and the value saved in exclude is vertex 1, 2. So this not equal predicate is not satisfied because it's indeed equal. So this does not satisfy the predicate, and this gremlin will be removed by the has step. What about these other two gremlins, like this one right here? Does it satisfy the predicate? The predicate says not equal to exclude. Is the current vertex not equal to the vertex saved and exclude? No, it's not equal. It's a different vertex. The vertex saved and exclude is v1 and it's right now on vertex v4. So not equal does satisfy the predicate and this gremlin will remain. Same for this gremlin on Peter. It does satisfy the predicate and will remain. So the next step is getting the values of the name property. The names will be Josh and Peter. So this traversal should give us the names Josh and Peter. Let's test it. And it did work out just as expected. And before we move on, I really want to stress on the difference between has, the has step, and the where step. Again, the has step filters by the property value. Does the property name equals Marco? If yes, keep the gremlin. If no, remove the gremlin. Here we're filtering by the object itself. Is the current object equal to the value saved and exclude or not equal? If it's not equal, keep the gremlin. If it's equal, remove. So again, has filter by the object properties, where filters by the object itself. Okay, now I'll move to the next traversal. It asks us to place a gremlin on every vertex in the graph, then traverse out twice. Well, placing a gremlin on every vertex is easy. We did this many times already. We just call g.v. This will place a gremlin on every vertex in the graph. And next we need to traverse out twice. So we will call the out step to traverse out once and then out again to traverse a second time. And since it didn't tell us a particular edge label to use to traverse out, so we'll just call out without passing any arguments. Usually we give the out function, we give it the edge label because we want to traverse out on particular edges. Here we want to traverse out along the created edge. But in this problem statement, it just says us to traverse out along any outgoing edge that's going out of this vertex. So we will just call out without passing any arguments. And let's picture this on the graph. First, I will delete these gremlins from the previous traversal. And the first step, g.v, we said this will place a gremlin on every vertex in the graph, but it will be just too many gremlins if I try to consider all the gremlins at once. So I'll just consider them one at a time. I'll start by considering the gremlin that will start at vertex 1. This one will be placed here by the first step and then will move out once along any outgoing edge, no matter what the label is. Doesn't matter if it's a nose edge or a created edge. We just called out without passing any arguments. So any outgoing edge, the gremlin will follow it. So one will follow this nose edge to go to the person named Josh, and another one will go here to the software that was created by Marco. And the third gremlin will move to this person that's related by a nose edge to Marco. And of course, the original one was split into these three gremlins, and there is no gremlin on Marco anymore. So this was the result of the first out step. The second out step, these three gremlins will continue moving out. Let's start by considering this gremlin right here on this software vertex. Well, this one it has no way out. There are no outgoing edges that are going out of the software vertex. So since this one cannot do the step, it will have to be removed. And same for this gremlin right here. It just has no way out. It cannot do an out step because there are no outgoing edges. So this one too will be removed. This one right here, it actually has a way out. It can move out of the vertex where it's at right now. So it will be split into two gremlins for the two outgoing edges. One will go here, and the other gremlin will move along the other outgoing edge. So we end up with two gremlins, one on this software vertex and one on this other software vertex. So one on vertex 3, one on vertex 5. Just so we don't forget that, let's write it somewhere. So the gremlin that started on the Marco edge ended up on V3 and V5. Now let's consider the other gremlins. The gremlin that will start on the vertex 2. Well, this one will be deleted very early because it can't even execute the first out step. There is no out of the vertex where it started. So this one will be removed right away. Let's place another gremlin here. Let's consider the one that will start on vertex 3. This one too has no way of executing the first out step. So it will be deleted on the first out step. Okay, now the gremlin on vertex 4, this one actually does have a way out, so it can execute the first out step. And it will be split into two gremlins. One will be placed on this software vertex and one will be placed on this other software vertex. Then each of these two gremlins will be asked to execute another out step. None of them has a way out. This one cannot go out because there are no outgoing edges. This one can't go out either for the same reason. So both of these gremlins will be removed. Okay, now there will be a gremlin on vertex that will start on vertex 5, will not be able to execute the first out step, so will be removed right away. The one on vertex 6 will be able to execute the first out step, will be able to go out to vertex 3, but then it has no way out of vertex 3, so will not be able to execute the second out step and will be removed. So it's only the gremlins that started at vertex 1 that gave us these two results, vertex 3 and vertex 5. All the other gremlins were removed before reaching the end of the traversal. So let's see if this traversal will give us the expected result, which is vertex 3 and vertex 5. I'll paste in the Gremlin console, and we did get 5 and 3. Okay, that's perfect. Now let's move to the next traversal. Well, it's about the same. Place a gremlin on every vertex in the graph, then traverse out twice, just like we did before. But here, we want to get the pass that these gremlins took to reach their last vertex. So what we got from the previous query, we got the last edges that the gremlins ended on. Here, we don't just want the last edges, we want the path that these gremlins took to reach the last edge, to reach the last vertex. So the traversal will be, the code will be pretty similar to what we did before with some additional steps. We want to save the results of these intermediary steps. We want to save where it started, the result of the first out step, and the result of the second out step where it ended. And we want our result set to show the path, not just the last edge. So show whatever was saved, these intermediary results that were saved. So what do we do to save the result of a step? Well, we saw this before. We use the as function or the as step modulator. So let's picture this on the graph. We know that only the gremlin that started on Marco matters because all the others one will end up being deleted before they reach the end of the traversal. So only the ones that started at the Marco vertex matters. So this one, the first step, g.v, will place this gremlin here, and of course will place all other 6 gremlins, but we don't care about them because we know they will be deleted and will not affect the result at all. So this was placed here by g.v, and then we call the as function, and the as function takes an argument, takes the name of the thing that you're saving. So we call as a, which is a step modulator, will not move the gremlin, will not cause it to do any filtering or even try to remove itself. It will only ask it to save the result of the previous step. The result of the previous step was vertex 1 for this particular gremlin. So it will save vertex 1 under the key A. So in its little head, it will write that A is equal to vertex 1. And this will be saved in the gremlin's head and will move along with the gremlin. And then the next step, we ask it to move out along any outgoing edge. So there are 3 outgoing edges. One is this nose edge, so it will end on the vertex 4. And another one is this other nose edge. It will end up on vertex 2. And the third outgoing edge is this created edge. So it will move to the software vertex. So now we have 3 gremlins. And before we move out again, let's save the result of this intermediary steps. Let's save where each of the gremlins is right now. Because remember, at the end of this traversal, we want to have the pass. So we need to save the result of each of these intermediary steps. So every time the gremlin moves, we will need to save where it's at right now. And again, to save the result of a previous step, we use as, and we give it the name that that will be the key for this value we're saving. So the first one was A, this one, let's call it B. So we ask each of these gremlins, we're executing this step modulator right now. We're asking each of these gremlins to save where it's at right now using the key, which is B. So each of the gremlins will add something to its memory. So B in this case is equal to V2 because this gremlin is on V2 right now. The result of the previous step is V2. This one is on V3. So under the key B, it will save V3. And this gremlin will save under B V4, where it's at right now. Okay, so Next, we will move them out again. This gremlin has no way out, so this one and everything in its memory will be removed. This one has no way out either, so this gremlin and everything in its memory will be removed. This one does have a way out, so this gremlin will move along the outgoing edges and everything that's saved in its head will move along with him. And if it is split, it will be split into two gremlins in this case. Each of the gremlins will have a copy of the data that was saved in the original gremlin's memory. So one will move along this edge, the other gremlin will move along the other edge. Okay, and we also want the result of this last step. We want it to be saved. Let's give it the name C this time. So we will say as C. The result of the second out step will be saved with the name C. So when we ask the gremlins to do that, this one will save C equals the vertex it's on right now, which is vertex 3. Vertex 3. And this one will save under the key C, will save the vertex where it's at right now, which is vertex 5. So each of these gremlins right now has 3 values in its memory, A, B, and C. This one has vertex 1, vertex 4, and vertex 3. This one has 1, 4, and 5. Okay, and then at the end of this traversal, we want to print the path. We want to print the values that are saved in A, B, and C. So to do that, to get values from the gremlin's memory, we use the select step. And select will take arguments which are the values we're selecting from gremlin's memory. In this case, we want to select all the values, A, B, and C. These are the results of each of the intermediary steps and the final step. So this should give us the 3 values saved on, and remember those are, there were a lot of gremlins on the way, but all of them ended up being removed and only these 2 gremlins remained until the end of the traversals. So only these 2 gremlins will matter and will show in the result sets. So for each of these gremlins, we want to print the values of A, B, and C that are saved in their memory. This should give us the values of A, B, and C, this statement right here. So let's test it in the console. And from one of the gremlins, we got V1, V4, and V5. This is 1, 4, and 5. That's the gremlin right here. And from the other gremlin, we got 1, 4, and 3. 1, 4, and 3. That's the result from the gremlin right here. And this is the path they took, starting from vertex 1 to reach the last vertex where they are at right now. Okay, that's it for this traversal. Let's now move on to the next traversal. It says group all the vertices in the graph by their label. Before we start writing this traversal, let's take some time to think more of what's meant by groups here and what's meant by grouping. Well, grouping is transforming a flat list of items into groups, each group having a header and a list of items under it. So if you have a flat list of items that looks like that, item 1, 2, 3, 4, 5, and 6, that's our flat list of items. And if we want to group these items, the result of the grouping will look something like that. Header A, for example, and under header A, we will have some of these items. And we may have another group with the header B. And under header B, we will have some more items. So grouping is transforming a flat list of items that looks like that to something that looks like that. Groups, each group having header and some items under it. And to do this operation, we need to specify at least one thing. We need to specify what will be used as the group header. What will be used to determine the group that each of these items will go under. And we may also specify some transformation to be done to these items before placing them under the group header. And I know it's getting a little bit too abstract here, so let's leave this and let's go back to our code. Let's try to write this traversal. So it says group all the vertices in the graph. So we will need to start by getting flat list of vertices of the graph. It will be g.v. This will get us all the vertices in the graph, a flat list for now. And we will try to group this flat list by the vertex labels. So to do that, we will use the group step. This will group the items, but we said that to group the items, we need to at least specify what will be used as the group header. So for that, we will use the by step modulator. By will tell us which property to use for grouping. Here, we want to use the property label. And it looks a bit strange passing label like that. Like normally you pass a string to by, which is the name of the property that you're grouping by. If you're grouping by the age property, for example, you would pass the string age like that, which is the property name. But because we're grouping by a very special property, the label property, so we identify this property using a very special way by just passing label like that. And label is actually a value of the t enumeration. So you can write it this way, t.label. Another special property that's referenced in the same special way is the ID property, for example. If we want to reference the ID property, we will say t.id, or we can just say ID without prefixing it with the enumeration value, because all the values of the enumeration t are statically imported by the Gremlin console. So you can just say ID or just say label, and this is the same as saying t.id or t.label. So again, this will be passed to the by, and now this flat list of vertices will be grouped by the label. So how our resulting groups will look like, we'll have a label and a list of vertices under it. Let's test this in the console and see what we will get. And we got two groups. We have the group under the label software, and it has vertex 3 and vertex 5 under it. And we have another group under the header person, and it has the vertices 1, 2, 4, and 6 under it. So these are the two groups that we got for the two labels that we have for our vertices. So the grouping was successful, and let's move on to the next traversal that will be a little bit more advanced. Here it says group all the vertices in the graph by their label and use the name property as the item value. So just like before, we will group the vertices by their label, but here the items that went under the group header, under the label, were just the vertices. But what if we want to apply some transformation to this flat list of items? We don't just want the vertices to go as is under the group header. We want the vertices to be transformed. We want to get a certain property value from the vertex before placing it under the group header. Well, to do that, we provide, let's not forget the backslash, we provide a second by step modulator. And here we say what will go under the group header. So label is the group header, and the second by will provide what will go under the group header. Here we want the value of the property name to go under the group header. So we will call by and we will pass name. And this will place the names of the vertices under the group header. And lucky for us that both person vertices and software vertices have a name property. So each vertex will have a name property regardless of whether it's a person or a software. Let's test this in the console. And we got, again, the software group header. And under software, now instead of having the vertices under the group header, we have some transformation applied to the vertices to get the value of their name property and place it under the group header instead of placing the vertex itself under the group header. So under the header software, we have the names LOP and Ripple. And under the header person, which is the label of the vertices, we have the names of the vertices, Marco, Vedas, Josh, and Peter. Okay, this was the last traversal for this video. I hope you guys enjoyed it. I'll upload this text file with all the commands somewhere and I will put a link in the video description. Thank you so much for watching. Please stay tuned and see you in the next video.